Log on, tune in, find out. Another good idea from Cambridge.
Left a very strong accent, really a great name in the history of experimental design. Everyone of you knows about the Wynn algorithm. I just speak in this way because we have some people from the outside, but this is only the tip of an iceberg. So we have here Henry Wynn, one of the most creative men in our community. Currently a professor at London School of Economics. Henry,
okay.
It's time for you.
Thank you very much. It's wonderful to be back in Cambridge. Thank you very much to Darius and Andrew, the organisers. I've been making this joke in the pub that on every single criteria, Cambridge is slightly worse than Oxford, but anyway, I was at Oxford. But half my family was here, so that's perfectly all right. I'm also extremely disappointed, but my name wasn't on the list of checks there. And I really want to know how much these so-and-sos are getting. Sorry.
Have you filled in your questionnaire?
Or maybe because I didn't fill in questionnaire. All right. And apologies to people who've heard approximately half this talk before, and many thanks to Andrew, who really set me up nicely, in the good sense. You can be set up in the bad sense, but set up in the good sense, because I will be talking about entropy quite a lot. So the way to take this talk is it's not really very much original, but as a tutorial on learning, Bayesian learning, which is really what one does when one wants to do experimental design. I have to say that this version's been knocking around in my files for several years. Some of this will be in Emmanuel's thesis, hopefully. We were going to do a joint paper. We kind of drifted apart a bit, so at some point it'll get written up. And also the references. I was fiddling around trying to get all the references in. There is a stack of references, so I'll try and get those attached to the file if it's loaded up anywhere, like here. So and I'll mention names as I go along. So there's one important theorem which the community ought to know, both communities, and I like very much the way the two communities are coming together. In a Bayesian version of a learning, which includes experimental design, we always expect to learn in a very well-defined sense. So we expect to learn, that's the expectation before we do the experiment. But of course in individual experiments, we may actually unlearn. So it's not always true, and I can give to what I think are quite nice counterexamples in a moment. There's some theory here, because this theorem we always expect to learn is true for a particular class of information functionals, which includes Shannon, which is the entropy, the one we've heard quite a bit about, includes Salis and others, but includes some others as well. And then once we've done this, we'll find a link with another, my favorite topic, one gets lucky occasionally, a link with majorization theory, which is a theory of inequalities, sometimes called rearrangements due to Hardy. G.H. Hardy was just up the road here, and Littlewood and Polya. So there's a nice link with something which doesn't seem to have any relationship with learning at all, but it has a very close relationship. And there'll be some examples here. I'll spend far too long on the beta distribution, because I spent because I spent a long time on it. You're going to have the results of that time I spent on it, so you can go to sleep at that point if you want. And then I'll come back onto experimental design, including what Andrew just talked about. So, first of all, we have a standard Bayes model. So this is just, I mean, I taught second year Bayes, but it doesn't mean I know any Bayes. I mean, this is a very rudimentary, simplistic version of Bayes, right? You have a sampling distribution and a prior distribution. So this is Shannon information. The expectation of a log is Shannon information. So the key thing in experimental design is imagine you've done the experiment. When you've done the experiment, you get the posterior, you can look at the posterior information in the experiment. You hope that it's gone up. Otherwise, why spend your money on the experiment? That hope is expressed in the fact that the expected value, this is before the experiment, always does go up. Right? So as you go into experiment and you're a very happy, paid-up member of the Bayes party, and you have your prior and your model, you can expect the information to go up. And we'll see later that in the definition of optimal experimental design in Bayes, you want that increment. Actually, you know the information you have, so it's a difference between the information you have now and the information after the experiment. You expect that difference to be positive, and you hopefully design the experiment so that the expected difference is as large as possible. Okay, so more general result is that there's a large class of information functions. This is Shannon, for a wider class of information. This theorem is not just true for Shannon, it's true for a wide class of information function. So, I'll say it again, for a wide class of information functions, and you're a Bayesian, before the experiment, your expectation is, and it's a theorem, that the information will increase. So this is an important theorem. It's not really in the theorem in books on experimental design, but if we're going to think of the sort of more subjective way of handling information, it is an important result. So here's a general definition of information. I call it IG. When G is log, it's Shannon information, and this is Rennie. Well, it's not really Rennie, it's Tsarlis. It's Rennie if you don't have the -1, you put something outside. But this is a great type of information. Thanks to many discussions with Anatoly and Luke for sort of discussions in and around, even the odd papers in and around Tsarlis entropy, so thank you to them. And for gamma, I'm taking it for gamma bigger than -1. Note that if gamma is very large, this is just like looking at the maximum of the distribution, right? Because the big bit will dominate. When gamma is 0, obviously I haven't put that in. When gamma is 0, this 10-bit like box Cox, right? This looks like box Cox. When gamma is 0, this tends to log. I didn't put that in, but that's Shannon. So Shannon is gamma is 0. Sometimes I use alpha later on, so I can see some misprints. I can predict my misprints from that. Anyway, so when gamma is -1, it's interesting. You take the expectation. It really measures. Anatoly tells me it's the topological entropy. It's the length of the support. It's the size of the support. So you just make. This is the sort of thing the computer scientists do. They love supports. Not quite so good at probability distributions, but they like support sizes. Okay. So that's the class of entropy. So I'm going to give you now the answer. What is the class of G's? Now, I'm going to say I spent a long time finding the answer, only to learn that it's a special case of result of de Groot's, and de Groot's result is you can take any convex function, that means convex over the density functions of the prior and the same function posterior. So this is a special case of result by de Groot, which came out in conversations with Emmanuel and maybe Andrew too. So anyway, it's the UGU. It's not just the G is convex, that's wrong. It's UGU is convex. And there's some papers in economics, which are in references, actually equivalent. The G, a very mysterious result. The G sort of 1 upon U is convex. If you differentiate, you find it's the same result. So here, this is very mysterious. How do economists discover that without really reading Shannon and all that stuff properly? It's just anyway, I think they've been put in their place by us arrogant statisticians, you know. Anyway, so here's the proof, the if part. Well, of course, you're going to fiddle around. This is me pretending I know any Bayes at all. I don't. I spent hours and hours just fiddling around with. You can go. At some point, you're going to have Jensen. All right, so some place in the if proof is easy. You're going to have a Jensen inequality. Don't bother to read it, but it's sort of all here, and you end up with Jensen, and that's your information functional. All right, so that's fine. The hard bit is the only if part, and I'm not going to give it. So what we have done is a special proof related to the information version. You have to you construct a special class of joint distributions. You assume that the thing is not true. You take some you take some limits, and it forces the function to be convex. So it's the if and only if is interesting. There's no other functionals of this G or UG class for which you expect to learn. Now let's before we go on, let's have two favorite ones. We'll do Shannon, and we'll do the maximum of the distribution. Before I forget it, because I probably will forget it otherwise, why don't we use, in difficult experimental design problems, just the maximum of the distribution as a new criterion in experimental design? So I'm going to sell that one today, right? Very easy, much easier than doing no integrals at all, just an optimization problem right in the middle of it. I'll come back to that later. But before I forget, I'll say that that's my favorite. Anyway, it's not true that the actual posterior information is bigger than the prior information. So I'll now go into my pantomime routine. I have to pick somebody, and I have to Andrew. Andrew. So you're the person you've lost. Oh, Andrew. It's A, right? A person A. That's good. A. Person A has lost their keys. They're almost certain that the keys are on their desk. That's probably where you leave your keys. A lot of the time, I do. So under most optimal design criteria, certainly under Shannon, it's really, I can now set up a optimum search experiment, which means look for my keys, right? So if my prior distribution is very strong, that it's on the desk, I look, it's optimal. Okay, so let's run the experiment. Andrew goes to his desk, and the keys are not there, right? Well, the prior information is very high because you've got a big spike sitting on the desk. Maybe his distribution that is in any other room in the house with probability, constant probability. So there's a famous, I love phrases in English which teach you statistics. If my keys are not on my desk, I don't know where they are. All right. So when he looks, the Shannon information goes down. Actually, there's a critical number of other rooms in the house for which the Shannon information will go down. Also, and it depends obviously on the probability of it being, P is the probability of it being on the desk, right? So etc. So it's an easy theorem. Actually, Anatoly and I worked this out years and years ago. We got this answer. And should have not your name on the paper, Anatoly, but you know, tough. You don't. Some you win, some you lose, right? This is a wonderful counterexample. No, but recall, something has improved. What has improved? There's less rooms to look in. And that's the topological entropy I just talked about. So one form of entropy has actually got better, gone down, or information goes up. But Shannon, hopeless, we got it. It's uniform, a slightly smaller support, but it's uniform, and Shannon, easy to show that Shannon's, I mean, if it was uniform on all rooms, it would be the lowest, but uniform on most of the rooms is pretty low, okay, afterwards. Now this is a more analytic example. And it came from the surprising, this is a bit like Milan, looking for nice counterexamples. So I want a nice counterexample. Pi theta given x is proportional to, this is my second year Bayes course, right? Here's my second year Bayes course. I write that. Every lecture I come in and write this on the blackboard, second year Bayes. So how do we make posterior flat? Because flat is low entropy. Well, if for some x, fx theta is roughly proportional to 1 upon pi theta, then you get 1 upon pi theta and pi theta, you get 1 for some x. So that means that x is likely to lead to a flat posterior and the information would have gone down. All right, so this is I started with that idea and just wrote it down on a piece and came up with this particular joint distribution. Here's my 1 upon pi theta sitting there waiting to do some killing, like here. And the joint distribution you can work going back through your second year Bayes, you can work out the joint distribution. Absolutely wonderful. And then you can do I0 is Shannon, I1 must be what we call Rennie 2. It's where you basically integrating f squared as opposed to f log f is okay. So you plot it and you come up with the example of this amazing result that with probability a half, now this is pretty bad news, with probability a half, the posterior information is lower. So with probability a half, you've unlearned, right? It works because remember the theorem is for expectation. This is just for probabilities. This is more like a medium-based thing. So there's a nice counterexample. Okay. So let's switch now into the theory of rearrangements. So what we want to do then is just for distributions, this could typically for the posterior distribution, or I'm doing it for general distribution. We say that one distribution is more peaked or less peaked than the other distribution if this entropy is less for all or more for all, or information, or entropy is minus information. So if I say entropy or information, just change sign in your head, right? So if it's less for one than the other, we call this is a partial ordering. Now, if you ask for something to be true for a lot of different functions, it leads to a partial ordering, not a total ordering. If I require it to be true for a single informational function, then it's an obviously total ordering. But this is for a family of information functions. Okay, so this we have here sort of coming from the nothing to do yet with learning, just from the we have a definition of a partial ordering which has a convex pi here. H is my UGU, all right, convex. So this should be UGU, because we turn it into H. So question is, is this equivalent to a well-known partial ordering on distributions? Can we take this and find it elsewhere in mathematics? Well, the answer is we can. But we have to learn majorization. So majorization, I'm going to put probabilities in here. Majorization says the sum of the two distributions, the sum of the distribution, so the sum of the pi's are equal to 1 for both. You order the probabilities. You take your stack of probabilities, order them. So you order it for one distribution, you order it for another distribution. And as you go up the distribution, from the sum of the biggest is, my biggest is bigger than Andrew's biggest. So the sum of the first two biggest is bigger than the sum of Andrew's first two big, and so on. And we say that this pi vector majorizes the pi 1 vector majorizes the pi 2 vector if that is the case. That's what I've said here. Or I see I've got it right way on 1 big and 2 or 2 big. I'm bound to make mistakes with inequalities, so don't say, oh, you got the inequality around the wrong way, because I'll probably just say yes. You're right, and I shall eat a large dose of humble pie, which I have in my pocket. So, all right. So there's equivalent conditions, perhaps the most famous of which is that the lower one, the flatter one, is a doubly stochastic matrix times the not so flat one. It's a smoothing. So the row sums are 1, the column sums are 1. And look, the thing we want is that this, for one, the sum of convex functions here, look, sum is less than for all continuous convex functions. So it's in the middle of majorization, you find our H function, our H condition, from the previous slide as one of the equivalent conditions of majorization. Now, the trouble is, we don't have discrete distributions, we have continuous distributions, but fortunately, there is a continuous theory of majorization for densities. And I will draw a picture because it's much easier, and I'm very bad at drawing pictures, so I will use the, if I can find the board rubber. Oh, thank you very much. So, it's easy just if I draw it. We know it's got something to do with peakedness, all right? So we're looking for, okay, so we take our, we take our density, take our density, we chop it up into very, very small slivers of probability, right? So here's this bit, and we put this bit here, and the next bit, and so that's, if we do it, so to speak, backwards, we can rearrange this density, so it's all stacked up to the left, and then it's a decreasing density, because the biggest probability is on the left. So here's one density. So you can begin to think of posteriors, if you want, priors versus posteriors. So maybe that's for the posterior. No, maybe that's for the prior. That's for pi. I've done this, produced a pi, rearranged pi. I'm now going to do it for the posterior. So, supposing the posterior, do the same. I do the same for the posterior. So, in a way, if when I've done this density here is more peaked, in some sense, then that's looking good for the posterior. That's basically, but what exactly is this definition of peakness? It's equivalent to stochastic ordering. So this is the definition, and this is the CDF. These pi squiggles are over here. So these are pi's here. These unrearranged are pi's, rearranged as pi squiggles. And if I'm integrating between 0 and c, I've got the CDF. And that's basically majorization, continuous majorization. Because I'm adding, remember, majorization, I was adding probabilities. Now I'm adding little bits of probability, and that's a CDF. So it says that and this is the most famous stochastic ordering, which is just ordinary stochastic ordering. So the ordering on peakness, which you get from information theory, for information for over all h's, is equivalent to the stochastic ordering, or first order stochastic dominance, if you want the fancy word, of the rearranged density. Because as Andrew Vey said, information doesn't care where the density is, so you stack it all up here and then compare it in the rearranged position. Okay, so that's basically the result. And there's lots of equivalent conditions. Here's the one we want, but there's some other nice conditions. This is my favorite. There's a favorite nice condition, which is if I slice, you can sort of see it by a kind of duality. If I slice it at the distributions at a particular level, then this distribution has, if one has more probability above the slice, so it's peaked, than the other one, then that's also fine. That's an equivalent condition. I mean, you just go to Marshall and Oaking book on majorization or anything on majorization, you have all these wonderful equivalent conditions. So if I'm going to compare two distributions, I can take any of the, compare with my prior, with respect to my posterior, I can take any of these equivalent conditions and when I'm computing, and use them to compare information. This is, remember, this is for all information functionals, all right? This is what this says. Okay. Partially in the univariate. Okay. So I'd say B3, what I call the slicing condition, is useful in examples because I can take densities and just chop them and see how much is above to get my peakness, all right? Anyway, now, one reason I haven't finished the paper off is because I need multivariate distributions, but the same thing holds. Now I'm chopping or looking at rearranged Gaussians. And what does rearrangement mean in more than one dimension? Okay, don't ask me that question, but I do understand what slicing means in more than one dimension. If I have two normal distributions, Andrew's is more peaked. If at any slice there's more probability above than mine, right? It's very easy with a bit of simple geometry rotations that it's equivalent to, obviously it doesn't depend on the mean, it just depends on the variance. Obviously, if the univariate normal distribution, one's more peaked. If the variance is less, hope it says right. I'm not going to look to see if I got it the right way round. And the same for the determinant. Well, log the determinant is the entropy, except for constants for the normal distribution. So if your distribution is more peaked by log determinant, it's more for normal. It's more peaked for any of this class of information functionals. So that's nice for multivariate normal. Don't shake your head, Anatoly. I can see it from here. Okay, so beta. So this is the nightmare distribution. You think you're going to have fun with the beta and knock it off in a couple of afternoons. Not true. So to explain this theory, this is the test bed. Why is it a good test bed? Because there's two parameters. If there's only one parameter, like for the norm we had a variance, the mean doesn't matter. For the variance you've got one parameter, you're going to get total ordering. You know, sigma goes up, entropy goes up, or sigma goes up, sigma goes down, information goes up, yeah. But for beta, you're comparing things of really radically different shape. So what is this ordering for the beta? Okay, now the first thing, which may be known to everybody in the room, but I didn't know it until I tried it out. If you've got two betas with the same mode, they intersect. Two betas with the same mode. One's maybe fat, the other's a bit fatter. They intersect at the same level. Very odd. So the slicing works beautifully, because if they're the same level, you slice. One starts off bigger, and the other one catches up. It obviously works. Well, obviously means several days, weeks thinking about it. But if they don't have the same mode, you're in deep trouble. But fortunately, at the same time, we started out doing some stuff in algebra. So you can use a little bit of algebra to actually find out, to describe this, or at least to do the rearrangement. Yeah, I mean, here's the beta. How do you rearrange it down onto to this? This is a beta. How do I produce the rearrangement? That itself, I've got to slice, integrate. That's an operations. When I do this, I slice at a particular level, which we call C. I take the difference in the abscissa there, and those difference in the abscissa becomes my new abscissa, x value, and you fiddle around and you come up with some unpleasant polynomial equations. Well, at this point, of course, we were doing quite a lot of stuff on algebra, so you can solve for the decreasing rearrangement, and you get this bizarre bow tie curve, and this decreasing rearrangement of beta 2, 3. This is this big high-dimensional curve which was on the last slide. This thing, this is one axis is Z, and the other axis is C, and when I plot that, we get this, and you can. There's a nasty little step here. You get a decreasing rearrangement, which is a little piece of a very high-dimensional polynomial equation. Right, now that was for 2, 3. You want to do it for 25, 35? That proves that it's an incredibly difficult problem, because that's the solution. You'll get a very high-dimensional polynomial. It'll probably have lots of bow-tied bits, and you've got to take the decreasing part. So, you know, it's not, so it has to be done numerically, really. This is me going through the elimination procedure, and so on. So I'm not going to, okay, so I did it. I laboriously, I'm not very good at programming, so I used Maple, but I did, you know, alpha, I took lots of different alpha betas and say, well, when does the domination fail? This is a partial ordering, right? I've got to take these pairs, alpha, beta, for integers, or ABs I've called them, easy to write AB. And at some point, they'll be incomparable, because this is only a partial ordering. Well, the partial ordering goes like that. When you hit 1, 3, and 2, 5, they're not comparable. This is bigger. This beta 1, 3 is better for some informational functions, but worse for others. All right. So somebody mentioned beta binomials have been mentioned at least once, maybe about Andrew. And this would be relevant to our beta. Okay. So I worked out the Shannons. One is so I took my two favorite Shannons. I did two favorite entropies, which is the max entropy, and the Shannon, and they switch over. All right. Of course, I was lucky that I could prove it with Max and Shannon. All right. And then you have these wonderful I've got a conjecture. If Max and Shannon are better for Andrews, then that implies the ordering. False. So even if I take all the Sazlik entropies for all alpha, it still is not equivalent to the full domination, because there's some information functions not in that class. All right. So this is now this should be A, and this is A. And this is B. Why it's U, V, I don't know. But it's so what is this curve? All right. 2, 3 is the only, 2, 3, this is, something's happening at beta T, 2, 3. So it's quite difficult to understand. I'm going to plot the ISO information for all other betas which have the same something, well, the same Shannon, the same maximum, and I'm going to plot this with lots of different information functions, and these are different, okay, so these are for different information functions. They're not comparable for 2, 3, but you can imagine that's not all information functions. There's a slightly, this Y class here, so I think the max and the Shannon in the middle, but I managed to compute, just for this one case, the outer boundary for all information functions. All right, it's a very hard computation, and I need help really. And so I repeat, these are the alphas and betas which have the same max, same Shannon. They cross over, but they're inside a general envelope which contains all, and there you see the partial. They, in some sense, that if I can do that for every point, I can fully describe the partial ordering. And here, these are just a whole bunch of equi-information. This is Shannon and Max. You see, they're not comparable. They don't all move in the same direction. So this shows for beta, Shannon and Max, not the same. Otherwise they'll all be parallel. Actually, if you do the t distribution, which I meant to have, I didn't quite get it transferred to the slide, but the t distribution also has the general t distribution, forget about a mean, it has two parameters, degrees of freedom and variance. You can also we can get these ISO information lines for those as well, and they're very nice. As degrees of freedom goes up, the sigma squared really takes over because it gets closer and closer to normal. But for low degrees of freedom, when you're near the Cauchy, they really do don't contradict each other, but they're not the same ordering. Clearly, they don't say the same thing about the distribution. Maybe degrees of freedom is a kind of fatness, and the sigma squared is, well, sigma squared, right? So, and so on. So out of this, we can stop doing the mathematics, and you're not as young as you were. You create general principles, right? So we have strong learning if the posterior. I've changed the this is my ordering now. If we have strong ordering if the posterior is more peaked than the prior for all information functions. That's what we really hope for. And it's partial ordering, and I've done the counterexamples. So partial ordering, otherwise partial ordering, so a partial learning is like the keys example where you improve on, you don't improve on Shannon, but there will be something you improve on because of the expectation theorem, and in that case it's topological entropy. We call that partial learning. So we always partially learn. You can always find an information function which does get better, but not for all, right? And then there's some theorem to do with the beta, which I won't go with. So those upper and lower boundaries. This is the definition. We can get those upper and lower boundaries, although they're very hard to compute, by some supremum and infimum operation, which is more like variational calculus or something. Technically, don't look at this, but think, I haven't done it for the multivariate T. I have no idea which is and I haven't done it for the Dirichlet. I have no idea. So my failure to find out what this ordering is for complicated multivariate distributions is why the paper's not yet finished, because I've got to do this calculation for your favorite distribution, and so on. Okay, so there's one nice little result you can get for beta. We learn with respect to the max, which is I have a great respect for the maximum as an entropy function. As I said, it will get a mention. And there is a theorem that as n gets large, you improve if the sample. This is some sort of coefficient of variation type thing. This is the distance of the mean. The mean expressed in terms of a's and b's, and the sigma squared expressed in terms of a's and b's. If the sample size is big enough, you learn. All right? Essentially. Okay, so there are theorems you can do, cheap theorems you can do like that. Okay, now I'm going to talk experimental design, which is what the conference is about. So we can take those definitions I had, and we can say, experiment is like super good if it gives us an improvement for all these information functions, or we can pick our favorite. We can pick our favorite G. Typically, people are using Shannon. But we could use max, and I said I'm going to sell max now so when the max is higher, the information is higher, or the entropy is lower. So please, somebody, PhD student, go ahead and do max experimental design in difficult problems. Something we could maybe discuss later. So maybe somebody in the room is already doing it. Now, thanks very much to Andrew, I'm going to talk about maximum entropy sampling. So there's two versions of it. This comes straight from my paper with Paolo Sebastiani. There's two versions of it. The version which is used a lot in computing experiments is you don't forget about parameters. You don't need parameters at all, this version. You've got places at which you're going to sample, Y's, and places which you haven't yet sampled. In computer experiments, as soon as you sample, you get the exact value, so you never need to look at that again. So you're only interested in predicting the unsampled sites. Maybe site is a good phrase. So what we want, as Andrew said, we want to minimize the pre-posterior over the sample of the predictive entropy of the predictive distribution for the unsampled observations. Now, it's critical if I'm going to say the answer is to maximize this bit, that this bit stays constant and is not design dependent. Well, that's the y together with its the sites, to give you the complement of the sites, is the whole field. It's all sites, and all sites don't depend on the design. So this is a fixed, big joint distribution of the whole population. You minimize this, you maximize this. It's just like that, just straight Shannon, right? And the theorem, which is a sort of theorem which Andrew mentioned, is that, hey, but you know, we like parameters, and there's parameters in there. You had a lot of parameters, thetas and phis and zetas and etas. So can we do this? It does maximum entropy, which started out being for prediction, also work for the parameters. Well, what we want then is that this is exactly your formula that you had. We want if this is fixed, then minimizing this, which is the Bayes, exactly the Bayes information criterion, except we're using entropy rather than information. That's exactly maximizing. This is the pre-posterior. We're trying to minimize, which is entropy, or maximize information. If this is fixed, then it's true again that maximizing the entropy of the sample is maximum. So the theorem depends on whether this thing is fixed or not. Because if it's not fixed, we have a much more difficult problem. But let's see if it's fixed. Now we use Shannon the other way round. We unwrap y theta in terms of the entropy of the parameter, which is fixed because that's the prior, it's not design dependent, plus the expected entropy of the posterior, of the predictive entropy of the data. This is the data, the true data, not the unsampled. This is the real data. This is the Bayes. This is the classic thing again, but for the parameters. Well, our models, most of the models this week have been like this, right? So theta only affects the mean. So the conditional entropy of y given theta just depends on the conditional distribution of the epsilons, and if it's IID, that's not design dependent, QED. But in the correlated case, if we go in and pick the design, of course, then it will if it's autocorrelated, the design will affect it a bit, and this bit will no longer be constant, and we can't do maximum entropy. But you could do the following: you could say, well, my epsilons are isotropic. I could take the design and shift it, right? Because in over the class of shifted designs, it's not design dependent. So I can do a kind of partial maximum entropy within a class for which it's true that the conditional entropy is not design dependent. So I could say a group action on doesn't change, and as long as the design is within that same group of action, the design is not dependent. This piece will not be design dependent. Otherwise, now, if in this case, the nice case we've been looking at all week, then it's true. Maximum entropy for prediction, which was the last slide, is the same as maximum entropy for parameter estimation. It works in both, which is a sort of miracle, which reminds us of the general equivalence theorem, but it's not the same. It's a bit suspiciously similar. And there is somewhere out there a proof where you prove one from the other, but I can't do it. And maybe it's all in Val Fedorov's head or Werner's head. Now, some more. I want to leave a bit of time for discussion. So I want to take Shannon and get it out there. They're doing some more work for us. So here are some. Why am I? I'm like a cat chasing the tail. Where's the, oh yes. What is this thing? Oh yes, it's my heart. Anyway, so this is cheap notation for the joint. Now, this slide is all about marginal distributions for some big data set, or some big, you could say statistics is all about marginal distributions, right? If you knew the marginal distribution of everything, you'd be fine. So so independence says the marginal of 1, 2 factorizes into two marginals. If I take logs, it is true that log f1, f2 is log f1 plus log f2. Shannon is expectation of log. So I just take expectations. Expectation there, we have the marginal information of 1, 2. splits, and this is the defining property actually of Shannon information, that this thing happens. That if you have, that when you have independence, if you read, elementary books in information theory, as you do your coin flipping, information adds up the stream. So independence which makes information add. So that's wonderful, right? We know that. But look at conditional independence. Now I'm wheeling in some here at my left elbow. I have some people who work on Bayes nets, all right? And they're going to supply for us lots of conditional independence statements. That's what they do. So here's the first conditional independence. This says that, this first one says that in their notation, this says that x1 is conditional independent of x2 given x3. Now, if you fiddle around a bit, second year probability again, that's the factorization. When you take logs, look, it's all additive. 1, 2, 3, so the same thing happens. Now let's be real Bayesians and do decomposable graphical models, right? Of which the most famous, interesting case is this, right? 1, 2, 3, 4, 5. So at each node you've got, this is a simplicial complex, nice algebraic object, beloved of algebraic statisticians. It's a hierarchical model, right? Blah, blah, blah. And what it says is, if I have this structure, I require it. It's a calling card. It's a passport to a particular type of factorization. So what it is that it's the marginals for 1, 2, 3, 2, 3, 4, and 3, 4, 5, and over the marginals for 2, 3, and 3, 4, the internal ones. And look again, we get 1, 2, 3, 1, 2, 3, 2, 3, 4, 3, 4, 5, 2, 3, and 3, 4. This beginning of this, I've seen this before. This is looking a bit like inclusion-exclusion lemmas. Well, that's exactly what it turns out to be. And it's easy to see with Gaussian. So, if you're a time series person, you like to express, actually we had some similar, one of those representations for, in Darius's talk, for representing spatial processes, or maybe it was Werner's talk. No, it was Werner's first model was basically a white noise, a moving average representation of your stochastic processor. Then it's clear that y is, I'm thinking this should be x really. This is x. It should be x. Did I have x before? Yeah. This is really x1, 2, 3. So I've still got 3 Gaussians. So any marginal has a projector associated with it. It's kind of obvious, right? Every margin has a projector which projects white noise down into that margin. So those conditions that we had before can be written in terms of projections. And look, 1, 2, 3, 4, 1, 2, 3, 2, 3, 4, 3, 4. These are actual projections, just simple old-fashioned linear projections. So the additivity goes through to projections. And if I remove the p's now and just call this 1, 2, 3, 4, this is really is inclusion-exclusion. Okay, this inclusion-exclusion of these sets. One, 2, 3, 2, 3, 4, and 3, 4, 5, and this inclusion-exclusion corresponds precisely to this. All right, and objects or models for which you can do this are called lattice conditional independence models. They're fantastic for handling information. So there's a class of Bayes nets, particularly in the Gaussian case, where where information just works like butter. You can just spread information on any subset, collect it, and so on. It works extremely well. Actually, while we're in the room, this is me not showing off because I don't know any quantum, but you notice back here that Bayesians, I scream at my friendly neighborhood Bayesians that this conditional independence is equivalent to commutativity of the 1, 3 and the 2, 3 operators, right? And of course, what does quantum theory do? It looks at a non-commutative case. So in a way, you can guess, without even opening the book, you can guess that quantum information theory which is your reading for the weekend, is about the difficult case. So the probability is the commutative case. This kind of buzz phrase, probability is a commutative case, quantum is the non-commutative case, and the difficulty of handling information in the non-commutative, or the Shannon, what happens to Shannon. So there's a little pointer. Maybe we should take our experimental design with a bit of help from Shannon and go into quantum experiments. That's another PhD topic. Okay, my final point is I want to, it's a strong message, and messages come out in many of the talks. Experimental design is not just about observation at points. We've seen transects, we've seen, I took some phrases down. It's about, I went to the web, and just before I came in here, Bayesian surprise attracts human attention, right? So there's a whole bunch of cognitive scientists using the failure of information to go down, just what I said. So failure of information to increase. I'm surprising. It was surprising when the keys were not found. So there's a whole literature. Believe me, there's volumes on surprise functions in Bayes. So maybe we should take a little bit. Maybe we should generalize our feeling about design, make it a bit more touchy-feely, as we say in English, all right? So here's a touchy-feely example. I'm not very well off, and I'm only going to accept data in a window, right? I'm not going to accept data, so I'm going to do selective sampling on any problem, any data in a window. If it's outside the window, I don't want it. I can fix the window before the experiment, all right? So we can go around putting windows. I think I'll have a bit of this data, I'll have a bit of this data. I'll leave my, we do, in the way you're doing it when you have a sensor, because that only collects data in a physical window. It can collect data unless it's self-activating sensor, a whole new other field for experimental designers. But sensors get data in windows, so why can't statisticians do that? Let's redefine it as selective sampling. So here is a standard Bayes problem, right? I want to estimate theta, use Shannon, and I pick a window, and I don't take any data outside the window. Where should the window be? Right? Well, of course, here's my prior distribution, like in the keys problem. I should put my window where I think the data is going to come. Absolutely wrong. The information theoretic says I ignore data where I think it's coming. I take data arbitrarily outside an arbitrary large symmetric interval. So the message is we extend information-based methods to general design problems, only use data which we know in advance is going to be truly informative. This should widen the entire, hopefully, the entire territory of experimental design and stop other people moving in on our territory. Yeah. There's a lot happening in computer science and so on. Okay, that's enough. Sorry I was a bit long.
Thank you very much. I'll have time for some questions. How about you, Andrew?
All right.
Okay, Milan.
Great talk. I just have a question relating this to de Groot information.
Oh, yeah.
Yeah.
So de Groot's theorem, which I didn't say properly, de Groot has a more general class, and he says it's any convex function on the density, which means it's a function which, if I mix two densities, alpha there, is 1 minus alpha f pi 1 plus alpha f pi 2. So it's a lot wider, and that's an if and only if 2. So that's the widest class. Of course, I'm more interested in information based, but your point about there's things in here which respect the locality in here, like variance.
That's convexity.
It's convexity. Isn't that convexity? Convexity in the space of distributions. This should be pi. This is so if I mix two distributions, that we define f, and then that also, you expect that also to increase. But I just specialized. I'm sorry, I did specialize in information-based. But anyway, it's good for some field.
Okay.
So why did you ignore other entropies in the second half of the talk?
Very good. So, it sounds I have a plant in the audience. The Shannon results, because I forgot to do the slide, I'll just do this. If I go back to the Shannon bit, this works for solid entropy. If I change that expectation to alpha expectation, gamma is gamma. I did solids with gamma. It's a gamma expectation with the expectation of some function integral, or the integral pi, but I change it to gamma plus 1 dx, or d theta. So gamma equals 0 would be Shannon, just straight expectation, integral against pi. So miraculously, the Shannon formula works for this extended entropy class. So everything I said does, but I don't know what this means. This strange type of expectation where I can reweight the probability with gamma pi. But we could use it. You can use solids. In fact, I'm suggesting you use the mode as a cheapo, right? So in some sense, the mode also has a limiting distribution. Yes.
So the entropy of the prior, the entropy of the posterior, and their difference are generally not invariant with respect to the model parameterization. But the expected Lindley information.
The expectant is always positive if you choose a functional in the group class or in my subclass.
Right, positive, but is it also invariant with respect to the one-to-one model parameterization? Because so Kullback-Leibler, expected Kullback-Leibler, which is expected average Lindley information gain, is a particular case of that alpha divergences that you showed
Yes.
in gamma alpha.
Yes.
So
I think it's the same. You know, I've thought about this. I think whether you use divergence or whether you use my rather called second year sort of primitive Bayes stuff that I understand, I think it's the same. I think it's the same. Yes.
If you decompose the phi divergence of Igor Vajda, you can make a Bayesian integration from the roots
All right.
by different, and always if you have a different divergence, you have a different density of each
All right.
integrates.
Okay. Well, I shouldn't.
It will be a sensitive in a Bayesian sense.
Yes, I should read the group stuff a bit more carefully. You're right. I think it's the same conversation probably. Thank you.
can you get any analytic formulas for your rearrangement distributions, like normal, for example? What
So
happens?
normal doesn't need to be folded to rearrange.
Half
it.
normal.
Yeah. No. Interesting.
Yeah, but what else?
No. If you take a multivariate normal, and which starts out in d dimensions, and fold it into one dimension, taking all the probability and being very careful about the Jacobian, so you don't. So you really should not compare probability in 2 dimensions and make it suddenly into 1 dimension without careful consideration of the Jacobian. If you do that, you get gamma distribution.
So you get gamma from normal.
You get gamma from normal if you go from d into.
You mean chi-square?
Not necessarily. What's it chi-squared? I'll check on that. I was doing it actually 2 days ago because I thought I might be. I think it's gamma. But rearranging the Richelieu, for example, into 1 dimension, I don't know. Hopefully, I think it almost certainly you go first to one-dimensional beta and then rearrange that. But that's very, very hard, as I just told you. And T, I want to do T as well. So there's a whole stack of distributions queuing up to have this therapy. All right.
Okay, let's thank Henry again. Let me say a few words to